Good morning everyone, I hope you're all well. Dr. Bennett here to take you through section 7.3, which is on distributed loads. So this starts on page 327 of the textbook. So we saw last time in the previous video that we were talking about centroids of areas, and what this allowed us to do was, if we have an object on a bridge, for example, we can find its center of mass, or the centroid of its area, so that we may consider the force as a result of its weight acting on the bridge as basically a point force, right? But what if we have a load applied across the entire length of a member? So the textbook goes through this example of these sandbags piled up on a beam. They are unevenly distributed, right? Which means that the load applied across the entire length of the beam is not linear, right? So what we're interested in doing is finding the force and the moment acting on this member as a result of this distributed load across the entire length of the member. And what we do is we describe this line, which describes how the load is distributed, by this expression W, which is called the loading curve, right? So we describe the distributed load by this expression, which is a function of x, and this is called the loading curve, right? And then we can use that loading curve to find the magnitude of the force and the magnitude of the moment acting on the member as a result of the distributed load by doing these integrations, right? So the magnitude of the force is the integral over the length of the member, and we integrate the loading curve, which is a function of x, with respect to x. And then to find the magnitude of the moment, we do the same thing, but now we also have a length associated with the force, right? Because it's a moment now, so we find the integral of x multiplied by the loading curve function. So let's now go ahead and have a look at a couple of examples of this. So before we get going with the examples, I've just sketched out the solution method. So, oh, by the way, I'm back on the English breakfast tea today. There's nothing like the taste of home in a crisis. So the first step, as always, is to draw the free body diagram. Then the next steps are to find the magnitude of the forces and moments using these two equations which we described above. And then once we know this information, the magnitude of the force, magnitude of the moment due to the distributed loads, then we can go ahead and apply the equilibrium equations to find any unknown reactions or external forces that we desire. So the first example that's basically described in the textbook, this active example 7.5, is a distributed load that has this triangular shape. Now, because that's a regular shape, we can just use standard results to work out the centroid of the area, right, like the textbook describes here, and therefore find the location that the force acts, right, because we know that it's 0 here and 100 Newton meters at point B. So if we find the x-coordinate of the centroid, we can work out where the point force acts and therefore solve this problem in a similar way as we described in the last class. So please make sure that you can follow this example from the textbook. What we're going to do here is have a look at a slightly more complicated example where the distributed load is described by a curve. So this is example 1. This shows a beam or a rod fixed into a wall, and it has this distributed load applied on it across its length in the downwards fashion. This curve is described by the load curve up here in kilonewtons per meter, and the question is to find the reactions at the fixed support at A due to this distributed load. So the first step, as we just described in the solution method, was to draw a free body diagram of what's going on. I have a fixed support at A, and therefore I have a reaction force in the X and in the Y, and also this couple which is preventing the beam or the member from rotating, right? And I can work out the Y-intercept by plugging X equals 0 into this equation, and I also know that when W is 0, then X is equal to 5, right? So I know this distance here is 5. So the next step, if I go back over to my solution method, is to use these two equations to find the magnitude of the force and the magnitude of the moment due to that distributed load. And that's what I've done down here. I've plugged in the equation for the curve, the loading curve, right? That was given up here in the question. So I've plugged that into this equation. I'm integrating between 0 and 5 because that's the length of the beam, right? And if I follow that through, integrate that equation, I should get the magnitude of the force is 10 kilonewtons, right? And we need to remember that this is in the downward direction, right? Remember how the distributed load was described initially, right, with these downward arrows. So we're going to need to remember that that's a downward force for when we apply the equilibrium equation, so that we get our signs in the right sense, yeah? So then we move on and do the same thing to find the magnitude of the moment. This time we apply the loading curve, multiply by x, because now we have a distance associated with this force because it's a moment, right? We're still integrating between 0 and 5 across the length of the beam. Follow this through and I get a moment of 18.75 kilonewton meters. So again, we need to remember the direction of this moment, right? And we also need to remember that when I initially outlined this definition, we're finding the magnitude of the moment about the origin. So that's critical when we come to think about the direction of the moment that we're finding over here, right? So if we're finding the magnitude of the moment about the origin using this equation, we've got the origin over here, we're going to get a clockwise moment, right? So when we go to evaluate our moments, we're going to need to remember that this is a clockwise moment and therefore will be negative in our equilibrium equations. So the final step, as we said over here, was to apply the equilibrium equations to find the unknown reactions, and that's what I've done down here. In the x direction, I just have FAX, so that's going to be equal to 0. In the y direction, I've got FAY minus this downward force due to the distributed load, right? So that's what I was saying about remembering the direction of this. And then we have to sum the moments about the point where we've evaluated the moments, right, to use this expression here. So remember again, this is evaluating the moment about the origin, which means that we have to sum moments about the origin and remember the correct sign for this magnitude here, right? So we said that it was clockwise, and therefore this is negative. I have the moment acting at A due to the fixed support, and then I also have a moment due to the reaction FAY at a distance 5, which is where this term comes from here. So if I solve that system, I get FAX equals 0, FAY equals 10, and solving for MA gives me negative 31.25 kilonewton meters. So just a couple of additional thoughts about what we were just talking about here with this example, is that we need to remember that this magnitude is the magnitude due to this force. So that when we go to apply the equilibrium equations and sum the moments about the origin in this case, we don't need to include the moment due to this force in this equation, because this term here is the moment of this force, right? That's what we calculated here, right? Which is why we don't include this with the associated length with it, because we've already included it in this, right? And to prove that, I have just a brief aside. So if we use the techniques that we used in the previous class, right, and we split up this distributed load into strips of width dx, right, and we have the height of these strips described by the equation of this curve, right, we find the areas of the strips dA as the height multiplied by the width, right, and therefore I can apply this equation, which finds the x-coordinate of the centroid by evaluating this integral expression. Yeah. So I integrate across the whole length of the beam again. I take x dA, right? This is dA multiplied by x, integrated with respect to x over the integral over a of dA, right? Work that through, and I find the x-coordinate of the centroid to be 1.875, right? So again, think about last time, if I needed to balance this shape on a pivot, this is where I would need to put my pivot point in order for the left-hand side to balance the right-hand side, right? So that's what I found here, the x-coordinate of the centroid. And that tells me where the magnitude of the force acts that I calculated over here, right? This is a magnitude of the force, and now I know where it acts. It acts at x equals 1.875. So if I go ahead and apply the equilibrium equations, right, I get the same here. Sum of the forces in x is FAX, and that equals 0. I sum the forces in the y, FAY minus the magnitude of the force, which was in the downward direction, so 10 kilonewtons, right? That's from here. But now if I consider what happens when I sum the moments, now that I don't have the moment only associated with the origin, right? So if I sum the moments about the origin this time, I have MA due to the fixed support at A. Then I have a clockwise moment about the origin due to the force acting at 1.875, right? So it's negative because it's clockwise. It's acting at a distance of 1.875 meters away from the origin, and this is its magnitude. And then I have FAY acting at a distance of 5, but this time in the counterclockwise direction, so it's positive. and I can solve that to get exactly the same as I did previously, negative 31.25. Or, now because I don't have the moment calculated relying only on applying this only from the origin, right, is that I can work out the sum of the moments from the opposite side, right? So now I'm evaluating the moments about point A, which is over here, and I have the moment due to the fixed support at A. Then I have this length, 5 minus 1.875, and the force is now giving me this counterclockwise moment, right, about A, which is why this is positive. And then if I calculate this, I get exactly the same answer as I did before. So that just proves how I can work out the x-coordinate of the centroid and then find the sum of the moments about either point. But this method, using this integral equation, only gives me the moment due to this force about the origin. Okay. So the second example we're going to have a look at is this beam with a distributed load from the textbook on page 332. This is worked example 7.7. We have this beam, again with a fixed support into a wall at point A. We have a distributed load acting on it for the first 10 feet of the beam. We also have these other external forces acting on it too. We have a 2,000 pound force acting upwards at the end of the beam, and also this couple of 10,000 foot-pounds acting on the beam also. So we're told what the loading curve is for the distributed load, right? It's given by that expression up there. And the question is to find the reactions at the fixed support at A, at the left-hand side of the beam. So the first thing that we do is we go ahead and draw the free body diagram. So we have a fixed support at A, therefore we have the two reaction forces in the X and Y directions, and also a couple preventing it from rotating. I've drawn on the distributed load curve. I've drawn on the dimensions, and I've also included these external forces over here too. So the next step is to find the magnitude of the force and the moment due to the distributed load, and we do that by applying these integral equations. So again, I've just plugged in the equation of the loading curve into these integral equations, and I should get the following answers. But again, I need to remember the direction of both the force and the moment. So you'll recall that the distributed load was described by these downward arrows indicating that it's a downward force. So I need to remember that for when I apply the equilibrium equations. And also, if we're evaluating this moment here about the origin, then I'm going to get a clockwise moment about the origin, or point A. So A is at the origin, right? I'm going to get a clockwise moment about the origin of magnitude 25,000 foot-pounds. So I'm going to need to remember both of those things when I apply the equilibrium equations, which is what I've done down here. Fax is the only force that I have in the x direction, so therefore that's going to be equal to 0. Summing forces in the y, I will have Fay over here, this 2,000 pound force over here, and I'm also going to have this downward force here due to the distributed load, right? So I should have three components to that equation. And then summing moments about the origin, which is also the point A, I will have the reaction force, I'll have the moment at A, MA, due to the fixed support, right? I'll have the magnitude 25,000 foot-pound moment in a clockwise direction. So remembering that this here is negative. I'll also have this 10,000 foot-pound moment acting on the beam. So that's already been resolved into a moment or a couple, right? So that's got no length associated with it. But it is in the anti-clockwise direction or the counterclockwise direction. So that will be included in this equation as positive. That's where this comes from. And then I will also have a moment due to this 2,000 pound force here acting at a distance of 20 feet, and that's also going to be in the counterclockwise direction, which is why this term is positive here. So if I solve that system, I should get the following answers. Please make sure you can follow all of that through. Check my solutions, check the worked example in the textbook, and let me know if you have any questions. So that's all for today. Keep checking Canvas for updates, keep checking my YouTube channel for videos coming up, and let me know if you have any questions or queries. Cheers, have a good day.